So I'm David Teitelbaum. I'm the program manager for the WPF graphics team. And you're all here hopefully because I'm talking about WPF graphics. In particular, I'm talking about WPF graphics features that we've introduced in the newest version of WPF, which is version 4. And again, I have a lot of material, and this slide deck probably rightfully would take over an hour, and I've got about 45 minutes. So I'm going to talk kind of fast. I'm going to kind of skip over things. If you've got questions, I guess, go ahead and ask me either during the talk or afterwards. I don't really care. You might have trouble getting my attention while I'm talking, though. But I'll go ahead and get started here. So what's new in WPF for version 4? Version 4, most of you are probably aware, beta 2 is shipped. We haven't shipped the final version yet, but the new graphics features. First and foremost, we have a new text rendering stack. There was a chorus of complaints about the old text rendering stack. People said it was blurry, complaints of that nature, and we've completely replaced it, and I think all of the problems should be addressed. So I'll go into a lot more detail about that later. We introduced something called layout rounding. People not only complained that text was blurry, but they complained that 2D geometry was blurry. So layout rounding should fix most of the geometry blurriness issues, the image blurriness issues that people have run against. We added something called ClearType hint, which allows you to enable ClearType when you're rendering to intermediate render targets. We added animation easing functions, which are a way to make your animations much more dynamic, much more organic looking. We've added Pixel Shader 3 support to our shader effect pipeline. We added a feature called cache composition, which allows you to create bitmap caches of a subtree of your application, and then you can render that as a bitmap, which is fully interactive and live. So it's a very powerful feature in terms of performance. We added something called visual scrollable area clip, which is a great name. And not only that, but this feature allows you to basically hardware accelerate scrolling in terminal services scenarios or RDP sessions, where you basically, without this feature, scrolling would require sending an entire bitmap of the scrolled content. Here you can basically do a scroll blit, and I'll go into more detail about that later. Other stuff we've added, we changed the default image scaling algorithm. We used to use the FANT scaler, now we're using bilinear image scaling. We've completely removed legacy bitmap effects. So some people will be very happy, some will be very sad about this. I'm very happy. And we've completely removed the fixed function rendering pipeline. So now you're either using the programmable pipeline or you're rendering with our software rasterizer. So to start off with text, because this is the big issue that everyone wants to see. The complaints about the old text stack revolved mainly about blurriness. People said that small characters were blurry. East Asian characters looked especially blurry, and a lot of people couldn't figure out why. I'll explain why later, but we fixed all this, and there was also a lack of rendering options. Basically, you had ClearType, and that was it. If you changed your system settings, you could get grayscale, but you couldn't get aliased rendering. You couldn't dynamically set it in your application. You couldn't make parts of your application render with ClearType and parts with aliased rendering, so we fixed all of that. But to understand why the text stack was the way it was, I want to go through just a real brief history of text on Windows. So in the beginning, Windows rendered with aliased text. It was aliased black and white, what we call bi-level text. And because it was aliased, you had to align glyphs to pixel boundaries. You couldn't have glyphs on subpixel boundaries. So everything was very sharp. If you had a vertical stem on a character, the stem was a black line that was pixel aligned, so it was very sharp. The curves and diagonal portions, of course, had horrible aliasing. You can see them on the W there. Later on, TrueType fonts were introduced. TrueType fonts were a big advance. They allowed arbitrary scaling of your glyphs, and the reason they did that was because they encoded all the glyphs as a quadratic Bezier curve. So the glyph was parametrically described, and you could render it at any resolution you wanted. There was a hinting language included in TrueType fonts, which basically told the TrueType rasterizer how to shift the fonts left to right in order to get them pixel aligned, how to shift the stems of the characters. It's actually a Turing-complete language that's embedded in the font. A lot of people don't even realize it's there. And the fonts have this other thing, which is embedded bitmaps. So with a lot of East Asian languages, there would be a bitmap substitution for small characters, and it would substitute aliased bitmaps in place of a TrueType rasterized font, just because it actually looks sharper to use the embedded bitmap than to go and render something even with ClearType. So going on, grayscale was introduced, and then ClearType was introduced. ClearType effectively triples your horizontal resolution on your display. uses the assumption that everyone's using an LCD screen. And the nice thing about LCDs is they have this very well-defined pixel ordering of colors. It's either RGB or BGR, depending on what kind of display you're using. So you can effectively address each subpixel individually. That's why people call this subpixel rendering, because you've taken the horizontal resolution of your display and you've multiplied it by 3 because you're treating the red, green, and blue color channels as separate addressable spatial pixels. So with the introduction of grayscale and then subpixel clear type, you could now put glyphs on subpixel boundaries, which meant you could get them more towards their ideal positioning. And I say ideal with my fingery quotation marks because the glyphs themselves specify a spacing for each character. When you're using something like GDI rendering, GDI aliased rendering, it'll scoot the glyphs left or right to be the closest possible position. But ClearType allowed you to put them in a more accurate position given the font's description. The problem with that, once it was introduced, was that the Windows UI had all been designed using the original pixel-aligned glyph alignment. And the actual layout with this ideal width rendering was different from the original rendering because it was more accurate. So you had all these UIs that were laid out based on pixels, whereas WPF, of course, has no real notion of pixels. It's all DPI independent. But we're talking back in the Windows 3.1, Windows 95 days. So they came up with a solution here because the layouts were different otherwise. They came up with GDI compatible with layout. And that allowed you to basically render ClearType rasterized fonts, but it had the same formatting metrics that that the original GDI layout had, the original alias layout. So it was sharper than the original GDI when you were rendering things like diagonal lines because it was using ClearType, but at the same time you had the same spacing, and vertical stems were all very clear. And the other nice thing about this was that it was actually sharper on a per glyph basis than the ideal width layout, the layout when you're using the actual glyph specified metrics. And the reason for this is because it would scoot things around so they were pixel aligned, whereas ideal width layout doesn't care about pixels, it just puts the glyphs wherever. And just so you're aware, almost every application on your machine is using this GDI compatible with layout. If you're using a standard Win32 application, almost all are using this GDI compatible with layout. So WPF, the first version, did not use GDI compatible with layout. This is a picture of Notepad. You can see that it's using GDI compatible with layout. WPF supported ideal width layout in its initial release, and that was the only glyph layout it supported. And I purposely chose these words here, hello world, with 3 L's, because I want you to see the L's in Notepad are all uniform, right? They're all identical. Whereas in WPF 3.0, the L's are all different. You effectively have a beating pattern emerging because you have the frequency of pixels on your screen and you have the frequency at which the fonts are describing the rendering of the L's. And so you get these patterns where the L's are not uniform because they're being positioned in exactly the right position. But in order to anti-alias them properly, you wind up with L's spanning 2 pixels. So why was ideal width chosen in WPF 3.0? There were a few reasons. The first was that it was actually a conscious design choice because words actually look better in aggregate if you look at them with ideal width layout versus GDI compatible with layout. If you look at like a flow document, it looks better on the eye to see it. The other reason is that GDI compatible with mode is not very conducive to having a scalable UI the way WPF is. You've all seen the scale sliders that are on Blend and all the other applications because WPF allows you to just put a render transform on the root node of your visual tree and then scale the entire application. The reason we can do that, especially with text, is because with ideal width text, the bounding boxes of each glyph scale linearly with a scale transform applied to it. Now that's not the case with GDI compatible with layout. With GDI compatible with layout, the bounding boxes of each character will shift left or right depending on where the pixels are in relation to where the glyph is on the screen. So that made it very difficult to make a scalable type UI the way WPF is using GDI compatible with layout. However, in 4.0, we do give you GDI compatible with layout. And this is actually a picture of WPF. WPF 4.0 using text rendered with GDI compatible with layout. The first thing to note is that all the L's are identical. And the other thing to note is that this renders almost identically the way GDI would. And I'm not going to say it is identical because you'd probably find small differences, but it's very similar. If you put them side by side, you can't really tell the difference in most cases. Something to be aware of is that switching to this mode, and by the way, this mode basically resolves all the clarity issues people have talked about. It's opt-in. The default is still to use ideal width layout. The reason we couldn't switch the default layout mode is because of compatibility reasons with previous versions of WPF. So there are a lot of changes that we'd like to make default, but they're not. So my recommendation would be to use ideal width layout. I'm sorry. My recommendation would not be to use. My recommendation would be to use GDI compatible with layout. I'll show you the APIs to actually enable this in a second, but first I want to show you a quick demo of what it looks like. So here is a WPF4 application. On the left, over here, you've got your ideal width layout, and on the right, you have the GDI compatible with layout. They look pretty similar. I'm not sure if you can tell looking at the big screen how much clearer the one on the right is than the one on the left, but it's substantially clearer. Something else you can see is that you can actually change the rendering modes. I can switch it to aliased rendering, and I don't know if you can see that or not, but it switched to aliased rendering on the right. On the left, it actually did not switch to aliased rendering. The reason for that is that ideal width rendering looks terrible. Ideal width layout looks terrible with GDI, or with, I'm sorry, I'm mixing up my terminology. Ideal width layout looks terrible with aliased rendering because you get glyphs that would span 2 pixels and you wind up with stems that would sometimes be twice as wide and sometimes would be just as wide as they're supposed to be. So as far as these new rendering modes that we expose, they're primarily exposed on the GDI compatible with layout. And I'll show you the APIs to enable all this. Going back to my deck. I'll show you the APIs over at the end here. So what I was just describing here was what we call text formatting mode. And when I talked about GDI compatible with layout, we call that display mode. You're basically optimizing for the display. Ideal mode is the ideal width layout I was talking about, where you're optimizing for the ideal positioning of characters. If you're going to have a UI that's going to be scaling around, you'd probably want to use ideal width layout. If you're going to have a UI that has fixed text on the screen, the way 99% of applications actually are, you'd probably want display text formatting mode. Something to note about display mode is that, as I was saying, the bounding boxes of the glyphs don't scale linearly as you put a render transform on this text. So the issue you'll run into is if you scale up display optimized text, we can't linearly scale up the font. So what we wind up doing is scaling up a bitmap of the font, which looks pretty horrible. So be aware of this. If you're going to have text that's going to be scaling around, you should be using ideal width layout. If the text is going to be of a fixed size on the screen, then use display. So going back to the other APIs that we've added, there was a big complaint before about text being blurry when it would animate. It would animate and it would get blurry and then it would get sharp again. You'd see this a lot if you ran like XAML and you grab the divider between the text and the content. The text in the text box beneath the display would get blurry. The reason for this is that WPF had an automagic, I call it automagic animation detection behavior. It would basically look at the aggregate of the transforms above your text, and it would look at it from frame to frame to frame. And if that transform changed, it would turn off vertical anti-aliasing of the text, and it would change the way the text was rendered such that it could render smoothly on the sub-pixel animation vertically. The problem with this is that most people didn't really care about that. It was basically optimizing for the case where you have a slowly animating block of text moving up your screen, and the idea with it, was that it would prevent the text from jumping from pixel to pixel to pixel. If you had geometry next to the text, the geometry would be moving smoothly, but the text would jump and you would see the relative differences and it would look horrible. And that was the thought anyway. So we added this automagic behavior in 3.0. The problem is most people didn't like it. In fact, very few people liked it. So we now allow you to explicitly control this behavior. And I'll go over to the API. We call this text hinting mode. The default is this auto behavior. Again, we couldn't change the defaults because we had to maintain backward compatibility. But fixed text basically always leaves the text crisp. It never turns on this blurry mode. And animated text always has the text in this blurry mode. So if you're going to be animating the text subtly on the screen, you should use this text hinting mode instead to automate or animated text. Or if you don't change that, it's going to use the default where it will look sharp when it's static and it will look blurry when it's animated. Now, moving on. We also, in adopting this new tech stack, we have support for the embedded fonts that these East Asian languages used. Languages like Korean and Chinese. So the East Asian language support is much better now. And we also have better foreign language support because our new glyph shaping engines support a lot more features than the old ones. We support things like diacritics now, much better than the WPF 3.0 shaping engines did. And the last enum here is this text rendering mode. You can decide, I already alluded to this, that whether you want to render aliased, grayscale, or clear type. So pretty straightforward. Another new API we added is a new text formatter constructor. It just allows you to select the formatting mode. So if you're doing low-level text rendering, you can use this and specify whether you want display optimized or ideal optimized text formatting. So on to the next feature, layout rounding. A common problem with WPF being a vector platform was that things would get positioned on subpixel boundaries, either because of their position on the screen or because of a scale above them. People complained a lot about blurry images, and there were several workarounds for this before, where you could turn on or change the image sampling algorithm to be nearest neighbor image sampling, which would kind of get you around the problem, or you could use some hacks to shift your images around. Layout rounding was introduced to kind of once and for all fix this, and this is a feature that Silverlight has also. It basically will take your geometry and it will snap it to pixel boundaries, both positionally, and it'll actually snap the shape of the geometries to pixel boundaries. So I don't know if you can tell again on the screen whether the images on the right are clearer than the ones on the left, but on my laptop, they look substantially clearer. So, and you can, I guess, I'll have these demos available later on if you want to take a look at them. And I do have a demo of this I'll show you in a minute. So this is not a graphics feature, it's a layout feature. So you have to run through layout to get this. If you're doing your rendering purely in a drawing context, you're not going to get this. You have to run through some kind of layout, because layout is when we go ahead and move the things around. We snap the positions and the sizes of things. This is different from pixel snapping. People are always asking, why not just use pixel snapping instead? We have this old API called pixel snapping. The thing about pixel snapping was it used guidelines and guideline collections, which were very confusing for a lot of people. And the other thing about pixel snapping was it wouldn't change the actual sizes of geometries. With layout rounding, if you have a rectangle, it'll actually snap the size of the rectangle to be pixel aligned so that every edge of the rectangle is clear. It's a property on UI element. You just set a UI element that use layout rounding equals true. And it's attached and inherited DP. So it'll actually affect the entire subtree when you stick it on a UI element. Another gotcha, like I said, this was a Silverlight feature. It's on by default in Silverlight, and it's off by default in WPF. My recommendation would be to turn it on the root node of your WPF application, just so everything looks crisp. And then if you run into trouble with animations not looking good, or if you have grid cells that aren't lined up quite right, you can turn it back off. But by and large, people are going to benefit by having this turned on. It will make your applications. I've had people tell me, I can tell a WPF application versus a Win32 application because the WPF one looks a little bit fuzzy or whatever, and this will basically eliminate that problem. Everything will look, I won't say everything will look crisp, lots of stuff will look crisp. And I've got a quick demo of this. Going back to my other machine. So here's layout rounding. This is the exact same grid on the left and on the right, and I hope you can tell. Again, where I'm dealing with pixels on the projector, maybe not matching up with what I've got on my screen. But on the left, you have no layout rounding, and on the right, you have layout rounding. And these sliders allow you to change first the spacing of these grid lines, and then I can also change the size of the grid lines. So you can see, or I hope you can see, that as I change the spacing, the grid lines on the left will actually land on subpixel boundaries. So every other grid line will, for instance, look blurry. Whereas on the right, every grid line is pixel snapped, and it's just one vertical row of pixels. I can change the thickness of these also. And again, you can see on the right, they're snapping to be integer pixel sizes. On the left, we're doing our per-primitive anti-aliasing. So because these things are landing on subpixel boundaries, they wind up having blurred edges. So it's a question of whether you care about sharpness or kind of the smoothness and the accuracy of the geometry that you're rendering. But it's worth noting that there's a good place for one or the other. It depends on what type of geometry you're rendering. But again, I would recommend you turn this on, and then if you have problems, turn it off, because most applications will benefit by having this turned on. Everything will look crisper. And moving right along here, we've added something called clear type hint. Now, a problem people ran into with WPF was they would render text onto intermediate render targets. And the intermediate render target, I have a list of them here. You've got things like drawing brushes, visual brushes, effects, where we'd spin up basically a render target texture off screen on the video card. We'd render content into it, and then we'd switch to using that texture as a source texture when we would paint some other part of the screen. The problem with intermediate render targets is they could introduce opacity. And an issue with ClearType, as I was talking about before, it basically triples the horizontal resolution. And in order to render ClearType properly, you would effectively need an alpha channel for each subpixel. In effect, you'd need 3 alpha channels per pixel on your screen. And I was told you actually would need 4 because you need 1 to do gamma correction. So the reality is the surfaces that DX supports and that WPF is using only have 1 alpha channel per pixel as opposed to 4. So if you're rendering ClearType onto an intermediate render target, we can only render ClearType properly if the intermediate render target does not introduce alpha. Now this is a mouthful to say, but the reality is the compositor does not know whether or not you're introducing alpha, so it always assumed you were, so it would turn off ClearType when rendering into, again, a visual brush or a drawing brush or a layered window or any of these things. So with ClearType hint, you can basically tell the compositor, hey, I'm not introducing alpha. You can go ahead and render ClearType correctly into my intermediate render target, and it will look correct on the screen. That's why it's called a hint. You're basically hinting the compositor to go and do that. The API is very simple to use, but there are some gotchas, so I guess pay attention to the next slide. It's just basically an attached property. You set render options like ClearType hint equals enabled. And the way it works is it affects the entire subtree until you hit an intermediate render target. And every time you introduce a new intermediate render target, you have to set this property again. It also does not work on text box. And this is an internal implementation detail that you should be aware of. It'll work on text block, it'll work on text runs, but it will not work on text box. So if you have a text box in a layered window, you're still going to only have grayscale font rendering. And it requires that you set a background behind the text. So even if you think there's a background, you have to be explicit about setting a background behind your text. Otherwise, it will still render with grayscale, and you'll think the property isn't working. I've run into this problem numerous times. So if you actually go and try to use this, it's worth looking into making sure that you have a background behind your text when you're rendering it into an IRT. So moving on to the next feature that we've introduced, animation easing functions. This is another feature that's also in Silverlight. I won't spend too much time on it. It basically allows you to have organic animations because it gives you, I'll show you a picture here, it basically gives you interpolation modes from start to finish. And the nice thing about easing functions is you can actually interpolate beyond the end point of your animation. If you see this graph here, their start value is 0, it's animating beyond 1, and the assumption here is that 1 is the completion value of your animation. So it's animating up to like 1.5, and this is sort of a bouncing easing function. So it's basically a modifier that you put on an existing animation, and it makes the animation look more organic. There are a bunch of these that are pre-baked into the platform. I've got a list of them here. You can write your own also. It's very easy to write your own. You just implement this easing function interface. And if you look at all you're doing here, you have this ease method that takes in a double and it returns a double. So you're taking a value from 0 to 1, and you return a value from wherever to wherever. So you're basically taking the system's interpolation value, and then you're outputting your own interpolation value. And you can actually output negative interpolation values. You can output values way beyond 1. So it's pretty flexible. I've got a quick demo of this to show. And again, I don't have much time for my talk here, so I'm trying to go through everything quickly. So these are both the exact same animation, except the top one has an easing function and the bottom one doesn't. So it's sort of a boring animation in itself. But if you had an easing function, it's much more organic. And that was 3 lines of XAML to do that. So it's a very powerful feature. And again, it's one of these things that you don't want to use gratuitously, but used tastefully, it can add a lot to your application. Moving on to the next feature we've introduced, we added Pixel Shader 3 support in WPF 4. Now, most of you are aware we added Pixel Shader 2 support in WPF 3.5 SP1 for our shader effects. The difference with Pixel Shader 3 support is there's no software fallback. There are a number of reasons for this. The biggest is that Pixel Shader 3 shaders are much more complex potentially than Pixel Shader 2 shaders. Pixel Shader 2 maxes out at 96 instructions. Pixel Shader 3 allows 65,000 instructions. So if we did a software fallback emulation of this Pixel Shader, you could have a single shader taking minutes to run. It would make your application completely unusable. So there's no software fallback for it. The nice thing about Pixel Shader 3 is that it has way more capabilities. It's got way more constant registers, the number of texture interactions. I mean, I'm just reading my slides here, but it's a much more powerful shader model. The thing to remember, given that there's no software fallback, is that your machine has to support PS3. We actually added a new API to query this, whether or not your machine supports Pixel Shader 3. But your machine has to support Pixel Shader 3, and the features in WPF that require software fallback will not have your shader applied. This includes render target bit mapping, printing, running over TS and RDP sessions, generating the base tile of a tiled tile brush, which is sort of a weird case, but it's an implementation detail. Or anytime your app is running in software, either because you've set the software flag on your HWin target, or because you've set the registry key to force software, or because your machine just doesn't support hardware rendering. So the APIs we've added are all pretty basic. You can query on the first one whether or not the Pixel Shader version is supported. You just give it a 3 and a 0, and it'll tell you whether or not PS3.0 is supported. We have a separate API to determine whether or not shader fallback is supported in software. The reason for this is it's basically forward compatibility for us. We can, in the future, if we found some way to quickly add PS3.0 support in software, we could go ahead and add it, and you could query for this property now, and in the future you would get a true, whereas now you get a false. The other thing we've added is this query for the max Pixel Shader instruction slots. The reason for this is because the Pixel Shader 3 specification is pretty open-ended. It doesn't crisply define what Pixel Shader 3 supports. So we allow you to query one of the more important details about a Pixel Shader, so you can, or about Pixel Shader support in hardware, so you can decide which of your Pixel Shaders to run. So now moving on, and I see I've got 17 minutes left, so I'm going to go kind of quickly here. We introduced something called cache composition. This is another feature that Silverlight has, though WPF's implementation is somewhat different, so it's worth noting the differences. It basically allows you to cache a live subtree of your application as a bitmap. Now the reason for this is that video cards are basically designed to draw textures on the screen, or they're designed for you to set state and throw a huge vertex buffer at it, and then it'll quickly process all the vertices. They're not optimized for the type of per primitive tessellation that WPF goes through when we're rendering very complex geometries. So the motivation for this is that we wanted to basically use this video card's fast pipeline as opposed to the slow pipeline that we're often forced to use when we're rendering vector content. Now the reason it's difficult to cache vector data, especially in WPF, is because our vector tessellations are position dependent in order for our anti-aliasing to work properly. As your vector geometry shifts across the screen, we actually have to retessellate it in a position dependent way, which is very expensive. Before this feature, you could basically roll your own bitmap caching if you really wanted to. A lot of people would go ahead and use a render target bitmap and render some portion of their subtree into a bitmap and then use that just as a not interactive bitmap cache. It was just basically an image that they would throw onto the screen. The other thing you could do was use this old tile brush caching behavior that we introduced. Basically, there was a property on render options, an attached property called caching hint. You could set that on a tile brush, and then you could set minimum and maximum scale and validation thresholds, and it would allow a tile brush to be cached. This didn't work very well, and a lot of people ran into a lot of problems with it. So I would discourage you from using this tile brush caching API and go ahead and use the real cache composition API, which I will get to very shortly here. So what does it look like? We've added a property on UI element called cache mode, and you basically give it an instance of a bitmap cache. And it's actually not a cache, you're giving it a cache descriptor. So when you create a new bitmap cache, you're creating a cache descriptor, and you're telling the UI element, hey UI element, cache your subtree as a bitmap, given the description I've encoded in my bitmap cache class. We've also added a brush, and Silverlight doesn't have this brush. It's called the bitmap cache brush. It's basically a cached visual brush. So it's like a visual brush that has its own bitmap cache. If you target it at a visual that already has a cache, then the bitmap cache brush will actually use the cache on the target. And there's actually, it's an interesting setup where the bitmap cache brush can have its own bitmap cache descriptor, and then it can have a different cache from the target cache. So it's super flexible, and it's also kind of complicated, so I would encourage you to read the documentation. The nice thing about these, again, is they're interactive, they're XAMLable, and unlike render target bitmap, the rendering is completely hardware accelerated. when you use these caching properties, we're basically spinning up an intermediate render target behind the scenes. We're populating it with our hardware rasterizer, and then we're persisting that IRT from frame to frame to frame. The typical cost with IRTs, the reason IRTs are slow and the reason we discourage you from doing operations that create IRTs is because it's very expensive to allocate, use, and then deallocate IRTs. WPF purposely does not persist IRTs around because we would just monotomically increase our video memory consumption until the system was exhausted. We're very frugal with our use of video memory. And so this property allows you to explicitly tell WPF, hey, my application is re-rendering something from frame to frame to frame. I want you to cache it as a bitmap. And you can actually have dramatic performance wins with this. And I'll get to the demo in a minute. The API is basically the way I described it. You have this bitmap cache, which is derived from cache mode. The reason we have an abstract cache mode class is because in the future we might add some other kind of cache, like a vector cache, something like that. But right now we've only got bitmap cache. It has a property called render at scale. You can basically choose the scale at which to render this cached bitmap. Now typically, or the way it determines the size of the cached bitmap is it looks at the subtree of the thing that the cache is applied to, just the local bounds. It doesn't look at any transforms above the subtree. It looks at the subtree itself and it says, what's your size? And then it goes ahead and creates a cache based on that size. Now this is important because in 3D, this behaves differently from the way a visual brush does. If you take a visual brush, point out some 2D content and then map it into 3D, the visual brush will project the geometry of the 3D bounds that you've got into 2D space, and it will figure out the size of that, and it will basically automatically size the visual brush. This caching API does not do that. It won't regenerate your cache based on the projected bounding box of your 3D geometry. So bear that in mind. So we have this render at scale property, so you can render it, your cache at some multiple of this target subtree's size. So basically, if I had the Surface application, like an MS Surface, a multi-touch application, let's say I have a text box that's really small and I want to scale it up to be full size, like full screen. And I don't want to lose visual fidelity once I've scaled up. And I know the initial size and I know what my final size would be if I scaled it up all the way. You can set this render at scale property. Looks like I've got 11 minutes left. You can set this render at scale property such that the bitmap you generate is as large as your final enlarged size of the screen. So basically, the initial size rendered on the screen will be small, but it's actually rendering from a very large cached bitmap, so it doesn't have to regenerate the bitmap as you scale the thing up. And we've got these other properties on the bitmap cache, snaps to device pixels and enable clear type. These would basically go together. The idea is that you want to be able to cache clear type text. Clear type only works properly if you pixel align the clear type rendered output. If you put it on subpixel boundaries, the clear type algorithm is completely broken because it was assuming a specific pixel layout when you rendered the text. So moving along, we have the bitmap cache brush. It's very much like Visual Brush. You point it at a target, and you can also give it a bitmap cache descriptor. We've also added a bitmap cache on Viewport 2D Visual 3D, which is the way you map live 2D content to a 3D mesh. This basically allows you to cache the 2D content and not have to regenerate it from frame to frame. And I'll show you a demo of this in a minute. Usage is very straightforward. Top line is one line of C#. You just set your UI elements cache mode to a new instance of a bitmap cache. In XAML, you can just do it again on a single line of XAML, or if you want to be more explicit, you can go ahead and set your render at scale. So here the render at scale is being set to 4, meaning your cache is being generated at 4 times the size of the target subtree. And I already explained all of that. Something that's very important to remember here is the order at which the properties on the UI element are applied. Now this is something we don't talk about much with WPF, but you have these UI elements that have, I don't know how many properties on them, and they're all applied in some specific order. Now conceptually, you could think of a UI element as actually being, I guess, 13 different elements. You have a render options element, and then you have a visual scrollable area clip element, and then an offset element, and then a transform element. And they're all going to be applied in some explicit order. We never really went out and said, hey everybody, this is the order these things are being applied in, but the reality is the order matters, especially if you're doing operations that don't commute. Let's say I clip something, and then I put, I'm trying to think of 2 non-commutative operations here. If I put perspective on something, and then I put an effect on it, I don't know. Actually, yeah, that would be an example. I mean, the order matters, and the reason I'm talking about the order here is if you look at this list of the order that these things are applied in, The composition cache is right near the bottom. It's right above the render data. Now the render data is analogous. It's basically the vector geometry that exists on a single leaf node in the composition tree. And then you have down here, number 13, child nodes. Child nodes would be all the children of the node on which the cache is applied. So the thing to realize here is if I have, let's say I have a text box, and it's got all sorts of vector geometry in it, and it's got children, and I put an effect on the text box, and I apply a cache to the text box. The cache will not cache the effect. In order to cache the output of the pixel shader on your effect, you'd have to put the cache on the node above the text box. And the way you can do this, a simple way is to just introduce a new node if you want to cache stuff above your cache, or else you can put it on the parent of the node that you're applying the cache to. I don't know if people are understanding this or not. I'm trying to be pretty explicit about this, but basically, you have to bear in mind what you're trying to cache and what you're not trying to cache. Now, the reason we didn't put the composition cache right at the top of this list is something like opacity. If you put the cache above opacity, then if I took an element and I cached it and then I changed the opacity on it, the change in opacity would actually be detected as a structural change in the cache, and the cache would have to regenerate itself every time you faded your element in or out. By putting the cache below opacity, I can cache an element and then change opacity on that element, and it's changing the opacity on the cached bitmap, so it doesn't have to regenerate the bitmap. So it's pretty explicit, and I mean, the reality is look at what your application is doing and then reorder things as necessary. But the order that these things are applied in was chosen because that's the most common order people do things in. So when you want to use this is obviously when you have expensive content that you'd be re-rendering every frame. Something else to keep in mind is that a composition cache will actually prevent these frame-by-frame intermediate render targets from being created and then destroyed. Now, a common case for this is if you have an effect on something. An effect will take brush inputs, and then it will go ahead and use those and apply the pixel shader to them, and then your output will be put on the screen. The problem with this is that effects will actually create an IRT for each input they've got. It will use it, and then it'll throw it away, even if your input is just something like an image brush, which really, I mean, you would think conceptually doesn't need to be in its own intermediate render target because it's already an image that's a texture on the video card. You should, I mean, for performance reasons, I would recommend you go ahead and try sticking a cache on all of your inputs for your effects, because typically it'll prevent the IRTs from having to be regenerated from frame to frame, and that will boost your application performance. This is the kind of thing where you should play around with it and see what works for you. Gotchas. Obviously, you don't want to cache everything in your application. The first instinct everyone has is, oh, I'll just cache every element in my application. The problem with that is you're going to exhaust your video memory really quickly. And caches are not always faster. If you have content that's changing from frame to frame, the cache is another level of indirection because you have an intermediate render target that you have to render into and then use that as your source texture. You don't have to keep reallocating the IRT, but you have to keep still rendering into it and then using it as your source texture. And that's not a cheap operation. Something else to keep in mind is that you should not set gigantic values for your render at scale property on the cache. The reason for this is that if you render into a gigantic texture, you'll actually blow out the fill rate on the video card. Because video cards have a finite amount of fill rate, rendering into a render target texture is typically slower than rendering than just drawing a straight texture into the video card, because render target textures are typically not swizzled, so you have worse video memory cache coherency. Also, reading from huge bitmaps is really slow. Again, you're blowing out your video card's texture cache. So you should basically make your caches as small as possible, but no smaller, I'll say that, so you don't exhaust your video memory. And you should understand the interaction between the brush cache that I talked about versus the element cache. There's actually a grid that is from the spec that's it's on MSDN now, that describes this kind of complex interaction as to whether or not your brush has a cache mode on it and whether or not your element that you're pointing the brush at has a cache mode on it. The reason we have this sort of complex functionality is you can imagine a scenario, like let's say I have a document that I'm editing. Like imagine I wrote like a version of Word and I've got pages of text on the screen. I want to cache each page of text on the screen with ClearType, and I want to be able to slide that thing around. But then I also want thumbnails of those pages on the screen. I want those also reading from cache bitmaps, but I don't want the thumbnails to have ClearType because the thumbnails text is already too small to have ClearType anyway. It wouldn't make any difference. So I can effectively set one cache mode on each page of text, which would allow ClearType to exist in that cache. And then I could point a separate caching brush at those pages of text, and that caching brush would not have ClearType on it. And it would be a much smaller render at scale. So it's a powerful feature, and you should play around with it. I've got a couple demos to show you kind of quite what you'll get out of it. The first one, I've got my CPU monitor over here. So this is vector content. This PopCan is defined entirely in XAML. And so I'm parsing the XAML. I load the vector content. I've got a bunch of these up here. And you can see this little cache text I've got. I can zoom in on the cans. And you can see as I zoom in on it that it's a bitmap I'm zooming around on. I can click on the cans and toggle the caching. So let me go ahead and get all the cans separated here. By clicking on the cans, and you can see the frame rate up here. I'm running at 67 frames per second. If I toggle caching on the cans, you can just watch the frame rate plummet as we start having to rasterize the vector content. And it's re-rasterizing all this every frame. I purposely have the cans basically subtly animating. So they're re-rasterizing every frame. But I want to get the point across that caching is a dramatic performance win versus uncached. So here's cached content. You can see as I zoom in on it, nice crisp vectors that we're rendering at the correct scale. But the reality is we're running at 6 frames per second. So you have to make a choice. Do you care about vector fidelity, or do you care about performance? In prior versions of WPF, you weren't given this choice. You were always given high fidelity vector content. So you now have the choice. And you can see if I have just one cache, it's pretty fast. I can zoom around on it. You can still see the fine details of the vector geometry, and I can pop it back to being the bitmap cache. And perf is obviously much better, but again, you lose fidelity. So it's up to you. What's your preference? Do you care about high visual fidelity, or do you care about performance? Actually, I have another demo. Sorry. So here's a quick 3D demo. This is cached 3D content. And what I want to show you is, if you're familiar with the way 3D content would render before, prior to caching, it would be regenerating, and you would see basically the characters would be subtly jostling up and down as the visual brush underlying this viewport 2D visual 3D was regenerating itself every frame, because it would. What was happening is it would project the 3D geometry into 2D space, and it would take the axis line bounding box of that, and it would use that as the basis for the size of rendering the visual brush. The nice thing about this cache is it's not regenerating the bitmap cache every frame. It's a single cache. So not only is your performance great, I've got 2% CPU usage, but the content looks crisper. It's not flickering around. Looks like I've got 1 minute left, so I'll get back to my talk here. So that's cache composition. We added something new, another feature called Visual Scrollable Area Clip. This basically makes scrolling over TS much faster in a certain set of situations. I don't want to say this is the cure for all slow TS situations, but it basically allows you to remote a GDI scroll blit. Previously, if you had an application with a lot of text and you scrolled even 1 pixel, you would have to send a bitmap of that entire text content over from the application machine to the display machine, because there was no way to remote the blitting operation. And there are a number of reasons for this. The biggest is that the way the compositing model works in WPF, you can't just take part of the scene graph and scoot it around because you have background behind it. GDI gets away with this because they don't allow as much flexibility with brushes. Back in the days when WPF had primitive remoting, this is the kind of operation that could have been done pretty quickly. But with the way remoting works today, you basically are splitting an entire bitmap of that text, unless you use this API. This API will allow you to do a scroll blit on the text on the screen, and it will only send a dirty region for the newly exposed part of text. So it works basically the way GDI scrolling works. There are a huge number of caveats to this API, and you should read the documentation very thoroughly, because if you have things like a background behind the text that can't be scrolled, let's say you're playing video behind the text, and scrolling the video would just create completely wrong rendering on your screen. You can't do that. So this is the kind of situation where if you have text over a solid background and you want good remoting scrolling performance, then use this API. And The last few changes we made that I'm going to talk about, and it looks like I'm 40 seconds over already. We changed the default image scaling algorithm from the FANT scaler to bilinear scaling. FANT scaling was very high quality, but it was slow. If you animated the scale of an image, it would actually stutter. Bilinear scaling is much faster. We've removed legacy bitmap effect support completely. Legacy bitmap effects will now no-op. This is obviously a breaking change, but it was done because legacy bitmap effects are basically dead. So you can now use shader effects if you want. There are a few legacy bitmap effects that are no longer supported that people are using, the outer glow bitmap effect and emboss bitmap effect. So sorry, they no longer exist. And we've also removed the fixed function rendering pipeline. Fixed function corresponds to DX7, DX8 class hardware. So we'll only render hardware accelerated now if your target hardware supports Pixel Shader 2 or better. So we've changed the definition of Tier 1 using the tiering API. So Tier 1 now requires Pixel Shader 2.0, and it has a 60 megabyte video memory requirement versus Tier 2, which has a 120 megabyte video memory requirement. And that's it. 45 minutes, and I covered everything. If there are questions, I'd love to take them. Thank you. Question?
Is there any statement you can make about the way things will look between WPF and WinRite and Win2D? You know, this.
Oh, direct write.
Yeah, direct, sorry.
It's actually interesting. WPF, when we're running on Windows 7, we'll use direct write as our text rasterizer. When we're not on Win 7, we'll use our own internal rasterizer. But the text should look very, very similar between the two. So there should not be much of a visual difference between the two. The quality is basically the same. So we'll actually use direct write when it's available.
Win 7, they're actually using the same rendering?
We're using the direct write DLL on Win 7.
Okay.
So there you go. Any other questions? Anybody? Nope. All right, well, thank you for coming.